Welcome back to section 3.5 on the chain rule. In this video, we're going to do theorem 3.5.2, example 3.5.2, and example 3.5.3. So let's start with theorem 3.5.2. If z is f of xy, is a differentiable function of x and y, and if x is g of s and t, and y is h of s and t, if they are both differentiable functions of s and t, then z, which is a function of xy, also depends on s and t, and it will also be differentiable. And the partial of z with respect to s is del z del x times del x del s plus del z del y times del y del s. Similarly, the partial of z with respect to t is del z del x times del x del t plus del z del y times del y del t. The generalized version of this is part 2 of the theorem. If w is a function of n variables, and if each of those variables is a function of t1 through tm, n and m not necessarily the same, then w depends on the t variables as well, and it will also be differentiable. And the partial of w with respect to the ith t variable, del w del ti, is del w del x1 times del x1 del ti plus all the way up to del w del xn times del xn del ti, which can be described more succinctly as a sum from j equals 1 to n of del w del xj times del xj del ti. Let's apply then the chain rule in example 3.5.2. So we have a function z, which is xy times e to the x squared plus 2xy, where x and y both depend on s and t as given here. We're asked to find z sub s and z sub t, and the instructions say that we don't need to simplify our answers nor substitute these s and t back into the final answer. So z sub s. Z sub s is another notation for del z del s, and using the chain rule, that is del z del x times del x del s plus del z del y times del y del s. We can start out, we'll do this all in line rather than working on this side. Del z del x is going to be the partial derivative of this expression with respect to x. That is going to be a product rule. So the derivative of the first is y times e to the x squared plus 2xy plus xy e to the x squared plus 2xy times the derivative of what's in the exponent, which will give us 2x plus 2y. That is del z del x times del x del s, the derivative of this expression with respect to s, which is just 2. Plus, now del z del y, so we have to take the partial of this with respect to y. So that is also going to be a product rule. So we're going to get x times e to the x squared plus 2xy plus xy e to the x squared plus 2xy. Now we have to take the derivative of the numerator with respect to y, which is going to give us 2x. That is del z del y. Now we have to multiply by del y del s, and the derivative of the y function with respect to s is just 1. And so there is del z del s, or z sub s. If we want to find z sub t, well, that is del z del t, which bears some similarity. So we've got del z del x times del x, not del s this time, but del t, plus del z del y times del y del t. And you see we can borrow some of the work that we've done before because del z del x and del z del y appeared in both expressions. So del z del x was in our first bracket here. So if we go up and grab it and bring that down, we can then just multiply by del z del t. Del z del t is the derivative with respect to t of the x expression, which is going to be just 1. Plus now del z del y. Del z del y was here. And so we'll go and grab this expression and bring it down as well. Del z del y times del y del t here is going to be minus 2t. So times minus 2t. Now this is normally would not be a final answer, but we're told not to simplify nor to substitute in. So it's a little strange maybe to have a partial in terms of variables that have some intermediate variables mixed in. But this instructions tell us that we don't need to bother to clean that up at all. Next example 3.5.3. This is about building a tree diagram. So suppose that we have w as a function of 3 variables, and each of those variables depends on 4 more variables. We're asked to give a tree diagram for these functions and use it to write the expression for one of the partial derivatives in terms of the chain rule. So we'll start in by writing w as, give myself a lot of room here because there are variables, 4 variables underneath. So if we have x, y, and z, that w depends on, each of those depends on 4 variables, s, t, u, and v, and so I can, again, the joys of working with technology rather than a pencil, I will just copy those all over. And then each of those branches, we remember that we write a derivative on. Now we want del w del v, which means that we are going to follow those branches down to get to v at every case. So I'm not going to label all the branches, I'll just label the ones that we need. So here is going to be del w del x, and this is del x del v, and we'll understand that the rest of them are labeled in a similar fashion. So if we want del w del v, then we want to follow these branches down and sum them up. So we're going to have del w del x times del x del v plus del w del y times del y del v plus the last branch down del w del z times del z del v. And there is the expression for the first partial of w with respect to v in terms of the chain rule. In the next video, we'll do example 3.5.4, which is going to be about using the chain rule to calculate second order partials.